And the LeetCode.
Alright, everyone, June 23rd. Alright, we also have to redo yesterday's because it's a better solution. We try to figure out how to use the monotonic array, but we were not able to, so we had to do that again. But let's try this one. Minimal number of k consecutive bit flips. Give a binary array nums and an integer k. A k bit flip is choosing a subarray of length k from nums and simultaneously changing every 0 to 1 and a 1 to 0. Turn the minimal number of k bit flips required so that there is no 0 in the array. If it is not possible, enter -1. Okay, so in this one I do 2. In this one, because it's 1, and then this will have a 2, so it's not possible. So we want to see how can we do so that everybody turns into 1. Size of 2. Okay. So we can turn these two and then all become 0. And then do this. Do this. Do this. Interesting. Minimal number of flips. K flips. Not K flips, it's K length. Length is K, and then we can flip. So if there's no 0, so a 0 must be flipped, right? A 0 must be flipped. Interesting question. Well, in order for it to work, so the last flip must be k number of zeros, right? Yeah. All right, so let's do it this way. We have some 0, 0, 0, 1, 0, 1, 1, 0, right? So let's say the ones on the edge, if it's a 0, then the only way to flip it is to flip this thing, because that's the only way to flip it. There's no other way that I can flip this. So if the front is a 0, then you're guaranteed you have to do this flip, right? You have to do this flip. And then you come to the next 0 here, right? Now to flip this, you can flip this, you can flip this, you can flip this. Depending on how long it is, you have different ways to flip them, right? And if, right, you flip this such that something to the left becomes 0, right? Then we say we have to flip them as well. Because like if you say, okay, I'll flip this, but I will destroy whatever has been flipped already. So I say on the left hand side is already flipped, okay? So I keep it in a certain way that everything to the left is already flipped, right? And now we have a first 0. So the theory is we always flip from the first 0 towards the right. We can change whatever is on the right hand side, but we don't change whatever has been flipped. Now the proof for this is if we do, which means if we say I'll flip these, so some will become 0 here, and this become 1, right? Then we need, because there's already 1, then we need another flip to turn these into 1, because they're already 1, right? We flip it so that becomes 0. And then let's say we flip them again so that everything can become 1. But if it's that situation, we can probably get away with it by, let's say, a 0, 1, 1, 0 situation, right? I can flip this and I can flip this, or I can flip this and then flip this. So I say maybe it's the same. Maybe it's the same. So I still don't have a good proof that, but I feel like it's correct. So we always, when we flip, we start from the current to flip to the right. So we'll make sure that all the zeros gets flipped once from left to right. And if we have a situation as 1, 1, some 1, and now we have a 0, 0, 1, something 0, and we always do this flip, right? We do this flip, now we have a new 0 here, so we push the 0 towards the right instead of going here. Because if we flip this, right, then we put a 0 in here, right? And these zeros, these 1s are useless because you still have to do this. Like you go left, you still have to go right, so these gets flipped twice. That's kind of the idea, right? Because if you don't say, okay, if we hear 0, we only flip it once, and then you just move on. If you don't do that, then you flip a 1, so something else might become 0, and you have to flip it again, so this one becomes 0 again. Then you have to flip it again, so that's kind of what I say. You will get some wasteful. So my idea is just go from the left to right. We'll flip the first one, we'll just flip him, and then yeah, 3 we just flip, so we look for the first 0, right, and then we'll flip it, okay, and then the next one will get flipped. So if it's a 0, then it's good. If it's a 1, then it's not good, right? So So this 1 will become 0, so this is the next 0. So I'll flip that. Right, now we have 2 flips. And how about the next one? And how do you know which one gets flipped how many times? That's a good question. Yeah, otherwise we'll be O(n) squared, so that's not gonna be that's not gonna work. Can we keep track of how many times each one? So the first flip, you have a range, right? So we know within this range how many times it gets flipped. And then the next flip will have a range. So we also know how many times. And this one gets flipped. So when we hit something, then we can query, right? So it's going to be, I think it can be a BIT because we just keep adding, right? We just keep adding. We say within this range, we getting flipped ones. So every time flip, which is +1, +1, +1. So every time we hit a 1, we'll see what's the current value, right? What's the current value? If it's a 0, that means it has not been flipped yet, right? If it's even number of times, that means it will remain the same. Yeah, it's basically even number of times, it's remain the same. If it's odd number of times, and so it's gonna be a BIT. All right, I'm not using Java for this. I'll have to copy BIT for this, and I am not in the mood of. Okay, let's try this. All right, so this is 623. Oh, should be 24. Damn it. Oh my god, this is so wrong. We're gonna do it again. It's 624. All right, it's 24. It's for 24. Yeah. All right, so we need BIT. Yeah, I don't care. I'm just gonna copy it. All right, so now we have BIT. So we need N, which is the largest, the size of the range, including min and max, the size of the range. And update the position and delta. Well, add the delta, yeah, query, so the query from 0 to max R. So we do 2 queries, and then we minus, so we know in query the sum of values from 0 to max R. What do you want to know? I want to know how many times that this one has been subjected. Huh. Yeah, because +1, everybody +1, right? So if I +1, update, I say that this position. So that's actually not true, because what I want is the whole range to plus. Oh, that's gonna be. This is going to be. Holy crap. I think this is a lazy implementation of segment tree, which I'm not gonna do. I'm not gonna do lazy segment tree, which I don't have to. Okay, I don't have to. So, yep, this is not gonna work. Yeah, because it's not updating one. You have to update all of them. All right, so we have bit manipulation and Q. Sliding window. Prefix sum. Prefix sum. That's an interesting hint, because the goal is to have the prefix sum to be the length of the nums, right? That was the goal. And the flip is basically just 10 to the 5th, so you cannot do it that way. The flip. A Q. Sliding window. All right, let's think about it, right? So if I have prefix sum, right? I have prefix sum, so I get k. I got a prefix sum. I say if the prefix sum of the first k is equal to k, then they're all ones, right? So I don't have to change anything. I can just start again. That is not true. Right, and then you have the next k. All right, so we do a prefix sum. We do a sum of each sliding window. Right, so the goal is by making these changes, right, we'll get all of them to be equal to. Let me think again. Fucking great. Wow, this one's pretty hard. Jimbo threw up.
What?
Jimbo threw up.
Food or hair?
Hairball.
Oh, scary. That's not throwing out, that's hairball.
Well, the food came out with the hairball.
I didn't even know it was hairball.
Because among the food that he threw up, there is a hairball in the middle.
That's why he closed the door?
Yeah, because preventing Jama from coming in. I already cleaned up everything.
Oh, thanks.
You're welcome.
Was all the food?
I think it's all the food. Need to give him lots of dry food.
Or maybe he feel queasy now.
Oh, he definitely does not feel well. I feel like he's yeah. He's resting now.
Maybe you shouldn't give him a lot of dry food. Maybe he's nauseous.
Okay. Let's see how he. Okay, we see his appetite. I'll give him the same amount then. Poor baby. I hope our next apartment doesn't have carpet. Man, this one's tough. Okay, so flip. Flip is turning 0 into 1 and 1 into 0, right? So we cannot just manipulate. Now we get a first k, and then we have some 0, some 1, so it's the sum is not equal to k, and we need to handle it. Okay, and then we handle it from a certain position on. Then what we need to know is what is the sum. Okay, so let's say this way, right? We have this and we have a prefix sum. Okay, we have a pre-sum. We have P0, P1, P2, you know, regular all the way to Pn. Okay, and then we go through nums and then we find the first position that's a 0. Okay, and then what we say is whenever we find a 0, we'll just do it. Okay, this is what we think. A little bit greedy there, right? Whenever it's a 0, we'll flip. And to flip, we cannot go one by one, right? What we need to do is find the k. So now this is the k, right? Now we cannot flip every single one, but what we can do is we will know within this k what's the sum of this k, because we have the prefix sum, right? So now we know what is in it. Basically, we know how many is ones, how many is zeros. So we'll flip them, right? We'll flip it. And after we flip it, we'll get a new prefix sum. Well, we'll get a new sum for this, right? If we get a new sum for this, but it's gonna change everything. Right? If it's a prefix sum, it will change everything. Well, we haven't used Q. So what the hell does the cube do here? So all we want to know, right? All we want to know is how many flips does the current one experience, so we can gauge whether we need to flip the current one again. So what if every time we do a flip, I know where it ends? So we put this index, right? We put this index, let's say in a queue, okay? We put this index in a queue. All right, so we have this index in the queue. I0, okay, let's say I0. We put I0 in the queue. And now we flip this one, which become 1, right? And then we'll look on the next one, and we'll check if it's smaller than this, all right? Well, this is gonna be a queue, gonna be a multiple, I1, I2, all the way. So these are like all the flips that we have done, right? And when we hit this, maybe we can binary search it, right? Because these are the end. So as long as the end is, and we don't have to worry about the front, because after we consider this, if we want to do it, so everything right, so this one will check if there's any end that is larger than the current, which means the current must be flipped by it. So if we binary search the current in this, if there's anything that's larger than it, would it be possible that we have something flipped? That's actually not possible, right? Because we can flip. We have lots of flip, right? So as we go through, once something gets smaller, right, we get someplace, and then we have something smaller. So these are just getting eliminated, right? We just eliminate them. Right, we just eliminate them. So we always check the front. We always eliminate them. So we make sure that everybody in this is bigger than the current. So we just check the size. We don't even need binary search. We check the size. Right, the size of this indices indicate how many times flip has happened for the current thing, right? And if the current is 0, and the size of the queue is an even, then it stays the same. And I can change it again and put one more in it, right? And then move on, right? And every time we'll that might work. Because all we want to do is to keep track. So if that's the case, we can actually do Java on this. So sorry, we need to remove this. Oh my goodness, we just done this and now we need to remove it. All right, so here's what I'm thinking about right now. So what I'm thinking is we need a queue. We can do a deck. Maybe integer flip and array deck. Right. And then we're just gonna go the number of flips it has done is the size, right? The size. So it's a 0, so it's just like that. And say rest is 0, so we say for int I 0 I smaller than actually be nums.length minus k. Because I just want to know how many times, so we say this is the last time, because if we pass that, right, if it's 3 and then do 1, is there 1 is 2? Okay, I think it should be a smaller equal to. Right, I think it should be smaller equal to. Right, so basically at this position, right, at this position, we'll check nums I, how many times has been flipped. So we say if it's even, then it has not been flipped. So we can say a boolean value. What we do is here, boolean has flipped false. Okay, it doesn't matter what it says because we're gonna do it here. So has flipped should equal to flip dot size, right? So if it's 0, that means it has been flipped. Actually, no, my bad. Should be equal to 1, right? If it's odd, that means it has been flipped. Now we say if has not flipped and nums I is equal to 0, or has flipped and nums I is equal to 1. Right, these two conditions. I feel like I can make this simpler, but let's just do it this way for now. Right, if it's not flipped and the current is 0, actually no, if the current is 1, or it has been flipped and the current is 0, that means it's already flipped to 1. So in this case, I will continue. Right, I'll continue. Else, so I can redo this. We can say if has flipped and the current is 0, right, has flipped and has not flipped and the current is 0, or it has flipped and the current is 1, that means it's 0. So this is a situation we have to do something, right? Okay, so what do? We'll flip it. So rest will plus plus. We'll flip it, and after we flip it, we will say flip ends dot add I plus k. This is the new and we need to add to it, right? But before we check the length, we have to say while flip ends dot is empty. If it's not empty, and flip ends dot peak first, right? If this is smaller than, if it's smaller than I, then flip ends dot remove first, right? So if it's smaller, then we just remove it, which means the previous end, it doesn't count. So remove. After remove, we'll do this, and then we do this, and at the end, we'll return rest. All right, so this kind of is my solution. Let's see if it works. All right, it doesn't really work. First is right, and then this one is bad. Oh, because I return rest is 0. 0 means, 0 means we cannot do any of this, right? So come out, so no flip has been done, okay? If no flip has been done, there's only 2 scenarios if no flip has to be done. One is, but how do we check? Well, okay, everything is 1, that should return 0, right? So we can do this. Sum is 0, okay? Then we say, yeah, let's do it here. It's just a special occasion, special case, right? You don't have to do any flip. You don't have to do any flip. One is you don't have to do any flip because it's already all 1. So the other is you don't have to do any, you cannot do any flips even though there are zeros in it, right? There are zeros in it. So what we are going to do is we say int sum is 0 for int n of nums sum plus equal to n if sum is equal to nums.length return 0, so special occasion. Otherwise, we shall return rest is equal to 0 if it's -1, otherwise return rest. Okay, so here is the idea, but not sure if it's correct. So we have this 995. So there is a bit greedy here. We will always flip the first, right? 0 encountered. I believe this will always result in the shortest, in the least number of flips, because if we don't do so, we will have to, we will double our efforts, right? Double our efforts in flipping some bits. Okay, now we need a mechanism to keep track of the number of flips a future, a bit, right, down the array has been subjected to. For this we use a queue. Now this comes from the hint, right, in which we save the right limit, right limit of each flip, right? Then before we consider each number, each position, each bit, we remove from the left all the right limits that are smaller than the current position, right? Since those flips do not overlap, right, the current position, then we can use the size of the queue to indicate the number of flips the current position has been subjected to. This will help determine what the current bit should be after those flips. Yeah. Yep, we call this ON, but let's see. Again, first we have to make sure that these are correct. Then we submit. Hopefully it passes. It does not. That was very bad. Okay. We have a 0, 1, and now we had a 0, right? So we flip it. So it becomes actually 1, 0. And then we go here. Okay, that's actually a good argument. So we have to keep going. Damn. Okay, that's a good argument. So we have to keep going. We cannot just do this, right? So we have to keep going. If, yeah, we do this, it has flipped. If it has flipped and 0 has flipped and this. So this is the current is 0, right? This is the current is 0. So now we need to check if I plus k is smaller than nums.length, right? Then we can flip. Then we can flip. Else, that means we have, so immediate to -1. This means we have a 0 in a non-flippable position. Okay, let's try this. Ah, that was bad. Really? Oh, I think it should be smaller or equal to. Because I plus k is outside, so it's smaller or equal to. Okay. Try one more time. Damn, that was bad. That was so bad. Okay, let's see. What happened here? We have 0, 1, 1, 0, 1, 1. So I flip this. I say 1, 0, 1. And I flip this 1, 1, 0. And I have here. How come I get 2? I should have the last one. Right? The last one. It should be a 0 because it should be flipped. And then it should return -1. Okay, let's see. So we flip and I plus k. Oh, I think it should be I plus k -1. Damn. Because that's the end, right? Ah, shoot. Alright, these are self-inflicted wounds. Unforced error. It's an unforced error. There we go. Right, these are unforced error. It doesn't count. If I had been just a little bit more careful, these can be avoided. Okay, so I think this is probably the solution for this. So, okay, let's read the solutions. All right, let's take a look. The order in which the flips are applied does not affect the final outcome. For instance, in the given example where flip in the order 0, the final array will be the same. This means that the solution can be approached by determining the correct indices to flip, regardless of the sequence. Really? Wow. Well, it's because it's exclusive OR. Yeah, because what matters is how many times you get flipped, not the order. That makes sense. Yes, we get this one, parity invariance. Subsequent flips with larger indices cannot alter the values of prior indices. For any given index I, one of the following two cases must occur to ensure there are no zeros. If num 0 is the 0, then I must be present in the flip sequence. And we flip nums yes. If I then I must not be in the flip sequence. Example 3. Flip num 0, 1, 2. Flip so 1, 2, 3. 2, 35, right? Flip 4, 5, 6. Okay. The duplicates gets removed. Okay, using auxiliary. Yes. Track the indices where a k-bit flip is needed. The strategy involves iterating through the original array while maintaining a variable flipped, which indicates whether the current bit is flipped. 0, making sure that each bit becomes 1. If the bit is 0 not flipped, we flip to 1. Okay, so now we can probably take a look. So we have flipped valid flips from past window, flip count. Something to return, right? For everything, if I is larger than k, decrease count of valid flips from the past window if needed. If flipped I minus k, valid flips minus equal 1, check the current bit needs to be flipped. Valid flips from past window. So how many flips from past window? Oh, that's the easy check, right? If it's 1 and the current is 1, then you need to flip. If it's 0 and the current is 0, you don't have to flip. Flipping the window extends beyond, so we cannot flip. Okay. Incremental count of valid flips. So valid flips from past window plus equal 1. So we keep track of how many flips that has happened. And we do flipped I, which means from I to the end, this one gets flipped. And the flipped count plus equal 1. So each time we'll remove, because I minus k does not help the current. It's out of the range. It's exactly the same as this one. I think the only thing difference is we can actually make this one simpler. We can say this is equal to, basically we can use a simpler, say this is equal to nums I. Other than that, everything else is the same. But except, now we do this, so we don't even need this part. This part is not necessary, right? This part is not necessary. So we do a deck, has flipped, we don't even need has flipped. Right, we don't need has flipped. And we do this, so we remove. Yeah, we remove. So instead of doing this, using an array, we will remove the and. And we don't need this. Has flipped, it's not necessary, right? So we just say its size. It doesn't need to flip. The current is 0, right? So current is 0. Yeah. Current is 0. Current bit is 0. And then we check. We'll flip. We do it. I think this will still be right. Yep. Okay, so this is surely need to. There's an update. Update. Use flip and dot size mod 2 equal to nums I to decide whether the current bit is 0 after all the previous flips. Also, since we are checking for unreachable, unflippable, right? Unflippable zeros, we don't have to do the extra check at the beginning. Okay, so let's submit this. So without the extra, I think this one will be faster. Oh, oh, I can just return 0. I can just return res. I don't have to. Yeah, you don't have to, because I handled all the round thing here. Because I go all the way to the end. Yep, that's the one. Eh. It's alright, but I like this one better. So let's do this. Yeah, this is definitely better. It's definitely better. And this is the same idea, right? Because you just record the previous and then you use the flipped array to keep track of how many flipped I did for the current, right? And then if it goes out of range, you just remove. Yeah, that's good. Using a deck, I think we're using a deck. We didn't use this. We used the size. Yeah, similar, right? Toggle the flipped state. Each time you do it, you toggle the flipped state. Else flipped Q append 0. You don't flip. Yeah, I like my way of doing it. I like to use the size and add the AND. Okay, what's the last one? This approach works in one pass without requiring any additional data structure. Current flips that represent the number of flips in the current sliding window of size K. To decide whether we need to perform a flip or not. If current flip is even and it's 0, okay. If current flip is odd and it's 1, we also need to flip the bit. It's the parity of the current flips to determine if the current bit needs flipping. We mark the current bit by setting nums. We mark the current bit by setting nums to 2, increment, and increase total flips. So the window slides if the element at the start was flipped with decrement. So basically, it's just to use, instead of using an external array, they're using the original. Yeah, I don't like this type of method. Right? I definitely don't like that type of method. Hello. Out of the range, and the previous one is equal to 2, because you just set it to 2 to mention that there has been a flip at that position, right? And then the current number of flips, decrement. And then you use the number of flips to decide. And it's this, otherwise you mark the current is flipped. So this is the same, exact same solution as this one, except you don't use an external array, you just keep everything in place. I like mine. Definitely like mine. All right, this is pretty good. This is pretty good. All right, that will be it. Yeah, it doesn't count as me solving it because I look at the hint. The Q helps. Prefix sum doesn't really help. I was going that direction, didn't give me anything back, so I didn't use this. Sliding window, a little bit. Didn't use bit manipulation at all. I think it's just a Q. The Q was the thing, the idea. And we locked down the solution of flipping the zero, the first zero we see, right? Then we know we cannot do O(n) squared. So we need to keep track of how many times a bit has been flipped. So previously, when we first started, we thought, okay, maybe that's a BIT, that's binary index tree. But that's not working. We checked, it doesn't work. And we thought it's gonna be a segment tree, a lazy implementation of segment tree, which I still believe it can work, but that's really gonna, it's too much memory and too much time. So then this Q comes up and I realize, yeah, if every time we flip, we put the end of the flip into it, right? And then when we hit any position, we just to check the Q, how the size of the Q, that will tell you the number of flips, and we use that idea plus a little bit more hints, and then we can get the result. All right, C# or C++ in game dev? No idea. Never done game dev. I did some small games in Python, but that's about it. Large scale game? No idea. But anytime you do C++, I feel like you're just asking for more problem. But I mean, in the game industry, I really have no idea. All right, anyway, that will be it for today. I'll see you guys tomorrow. Adios.